Hello everyone. In this video we are going to briefly talk about the dry or Coulombic friction, which as you probably learn in your physics, it's due to the irregularities and ups and downs on the surfaces of the two objects in contact, which when you move one object with respect to the other, these irregularities would hinder the motion and would apply a force opposite to the potential or active direction of the motion. So that's one of the main reasons that this Coulombic friction comes to existence. But the other reasons we can talk about, so that's what we call surface roughness, but there are also deformations. So definitely some of these irregularities have to be, when the two objects move, there will be some deformations as well in this shape of the parts of the body near the contact surface. So we can include deformation in that, but one of the other reasons which we probably do not discuss a lot in elementary dynamics is surface adhesion. So the matter of fact is, when two objects are in contact, and the more you leave them in contact, or the smaller the sliding velocities, they have a better chance for forming intramolecular bonds, and that leads to adhesion. So there are some molecule bonds that are formed here between the layers of the top and the bottom object, as you can see. And these molecular bonds, or surface adhesion, is another thing that would resist the relative motion of the two parts, because you have to break those bonds. So it's a combination of the two that we study. And the important laws of dry friction that were mentioned by Amonton and Coulomb is, they say that the force of friction is directly proportional to the applied load. So if these two surfaces are pressed together with some force NP, whatever you want to call it, so let's say you fix the bottom surface and you just move the top surface, but when this top surface is moving with respect to the bottom surface, so that is your V relative, then there is some load that is pressing these two objects together. The minimal is the weight of the top part, okay? So if I call this force applied from the top to the bottom N, okay, which comes from, at least, as I said, the weight of it, then it says the friction force, if I call this friction force here, acting on the top object to the right, if I call it F, it says this F is proportional to N. Okay? Now, in the Coulomb's formula for friction, we assume this proportionality is linear, which means F is equal to some constant times N, and we call that constant mu, or coefficient of friction, whether it's static or kinetic. But in general, really, unless some specific conditions apply, this simple linear relation is not 100% correct, and there are limitations to it, which I don't want to discuss with details right now. But for now, for many simple applications, we can assume that this proportionality is linear. The second law says the force of friction is independent from the contact area. Okay, so for example, if you have this fixed surface and you move an object like this on it, let me use a different color. So if you move something like this on it, or if you move something like this one, as long as the normal force that is applied is the same for both cases, so if the normal force from the surface to the object or backwards is N here and the same N here, so if this is N1, this is N2, it says that if they are moving, let's say, to the left, then the friction for both of them is to the right. So this is F1 and this is F2. If they both have the same material, these boxes, if they both have the same material and the same condition, then F1 can also be said to be the same as F2, and it does not matter that the contact area is this much or this much. Okay, while in reality, again, for some applications, this assumption is not true, and one major limitation is adhesive tapes. Okay, and adhesive tapes, not only they violate the second assumption, they also violate the first assumption. And so when you have a surface and you put some adhesive tape on it, you know that here, if you want to move this adhesive tape, it definitely gives you some friction, and that friction does not need really you to press this adhesive tape down to the surface. And you know, the weight of this adhesive tape is quite negligible. So here definitely this F and N, they do not have a linear relation, and without really much of N, you have a significant F. Secondly, the more surface area, the more contact the adhesive tape has with the bottom surface, the more friction you are going to get. Okay, and the reason is, as I said, when they mentioned these laws, their assumption was really that friction is only coming from these irregularities, not from these bonds. But these molecular bonds is quite more recent compared to this irregularity theory for friction. And so when you combine the effect of them and you call it what? You call it dry friction, then it's mostly these irregularities that follow this first and second law, and to some extent the third law, which I'm going to discuss in a second. But these molecular bonds are completely different. Their behavior is different. They definitely depend on how much of contact area you have. They do not super majorly depend on the normal force, and their formation and their strength does depend on how fast you slide the parts together, how long they are in contact, and so on. While for irregularities, that's a separate mechanism. Finally, the Coulomb's law of friction, or the third law that is important, is say that the kinetic friction, which means when the two objects move with respect to each other, that amount of friction is independent from the sliding velocity, which, as I said, it means regardless of how fast I'm moving one object with respect to the other, the amount of friction is going to be the same as long as I keep the N force the same. Okay, which again, that's not necessarily true. And we can show that in reality if you basically plot the friction force due to sliding, we call it kinetic friction, versus the relative sliding velocity, the relation is not going to be like constant. And actually, for most of the material, it has a slight drop. And the reason is, as I told you, when you move the objects faster, you don't give them too much time to form these molecular bonds, and so that portion of the dry friction, that contribution of those molecular bonds, is not going to be as significant. Okay, so as long as we only care about these irregularities and there is not too much of adhesion, yes, it could be quite constant, but when the adhesion plays a role, which many of the times it does, then it causes some drop as the relative sliding velocity increases. So each one of these laws, they have some limitations, but in general, you can show that I can apply a formula like this for many simple applications where F is a constant mu times N. N is the force that is pressing the two surfaces together. F is friction, and mu, we call it coefficient of friction. Now, this coefficient of friction, it does depend on the type of the motion, whether there is a motion at all or there is not. So let's say if we perform this experiment, let me show you. Well, let me see. Seems like, yeah, something is on the way. So here, this is the experiment we do. We have a box on a surface. It has the weight, it has a normal force, and we try to push it to the right, so friction is going to be to the left. Now, you know, if your force that is pushing the object is not really a large force and this object is quite heavy and or the surfaces are rough, initially with a small amount of force you probably cannot easily push or at all push the object, and so the object does not move. So as long as the sliding velocity is zero and it does not move, we call it static friction. Okay? And the more force you apply, you see the surface try to match your force and try to neutralize your force. So the surface is also capable of generating more and more friction, and it keep up with you until some limit. That limit is the maximum friction that the surface can generate. And for that maximum static friction that the surface can generate, we can write that as a constant we call mu s, or coefficient of static friction, times n. Okay? And there is also a name for that term. We call it traction. So this term, this is the maximum static friction, Fs max. This guy is the maximum static friction. We also call it traction. And it doesn't mean that as long as the object does not move, the friction below the object is always mu s times n. It's not. It only happens when the object is about to slide, when the surface is about to give up matching your force and say, hey, I cannot make more friction than this. That is when you're about to push the object and slide it. That is mu s times n. But in general, as I mentioned, for static friction, which is any region like here, there is no simple formula. Okay? You have to determine that from static equations. Let me give you an example. So, numerical example. So let's say the weight of this object is, let's say, 10 Newton. Okay, let's use simple numbers. So if there is no other vertical force, the normal force is also 10. And for the sake of just example, let's say mu s is 0.5. So it means that mu s times n, or the maximum static friction, is going to be 5 Newton. Now, if I apply 1 Newton here, how much of friction does the surface give me? Well, that's one of the mistakes that I see some students make and say, hey, this is equal to mu s times n. No, it's not. The friction from the surface is just going to be enough for the object to not move in the horizontal direction. So if I call this direction x and I call this direction y, then I need to find the friction by saying sum of the forces in the x direction, which is F minus F, or F static if you would call it, is equal to 0. Okay, and from here your F static is going to be equal to the pushing force, and it is going to be 1 Newton. Okay, so the static force is going to be equal to the forces that are trying to push the object, and it just is big enough to cancel them, and it can keep up with you. So now if you make this 2 Newtons, push a little bit harder, then friction will generate 2 Newton. If you do 3, it goes 3. You go 4, it goes 4. You go 5, it goes 5. But once you pass 5, which is the maximum capacity of generating friction, which again we call traction, the surface cannot keep up with you anymore. So when you go 6, now the surface cannot go to 6. And that's where your force is now more than all that the surface friction can exist, and now the object starts to what? Slide. When the object starts to slide, we call it what? We call it kinetic friction now. Now in this area, I can say that the force of friction, if I call it with Fk, this is equal to a constant we call mu k times m. Here, this is Fs. There is no formula for it. We have to find it from equilibrium. For Fk, there is a formula, mu k times n, and this mu k, we call it coefficient of kinetic friction. This mu s was coefficient of static friction. Typically, mu k is less than mu s, which means when the object starts to slide, you're going to have a drop here. Okay? Because this is mu k times n, that is mu s times n, that peak point. So you will have a little bit of drop in the friction. Typically, it's not always the case that mu k is less than mu s, first of all. And as I said, this mu k also is not constant really. In this model here, which is not realistic, we assume that mu k is constant regardless of how fast we are moving it, although here the horizontal axis is n, not v. So yes, against n, I can say mu k does not depend on n, although again, it's not perfectly correct for some application. But for simple applications, we can say this mu k could be a constant, not a function of n, but actually it is a function of v. So if you push the object and the part accelerates, right, because now when the object starts to move, what happens? Now this is going to be f minus fk when the object moves, and f is 6, and fk is mu k times n. And let's say again, mu k is like, let's say 0.4. So this is going to be 0.4 times 10. So this is going to be 2. And this is equal to m times ax. And let's say, for example, if m is 1 kilogram, then you will have ax of 2 meters per second squared. And when you get a, if you start from a stationary position, it means you are going to get velocity, and your velocity is going to what? Your velocity in the x direction is going to go up, and that means your mu k should what? Most of the time drops. And when it drops, it means this force is going to go down a little bit. So even if you keep your capital F force constant, it means your total force is going to go up, which means A is going to go up, which means your increase in V is going to be even larger. Okay? So your acceleration goes up a little bit as the object starts to gain momentum. So if I want to summarize this diagram, again, in the static case, there is no formula for the friction. You have to find it by equilibrium. In kinetic case, we can assume that it is equal to mu k times n. Mu s times n is just a capacity, a maximum friction in a static position that the surface can generate. We call it traction, and it only happens when the object is about to slide. Okay? So please keep those in mind, as I have seen over and over in my classes that some students make mistakes, and anytime the object is static, they say the friction is mu s times n. No, unless it says the object is about to slide, mu s times n is not going to be used. Okay, and now as I mentioned, in general, most of the times mu k is less than mu s, but not always. There are cases that it could be equal, like if you have a Teflon to Teflon contact, okay, then you can see that mu k and mu s are equal. The other assumption that sometimes is mentioned is this mu is always less than 1, but that is not true. There are cases that mu is bigger than 1, between 1 to 2, sometimes even as big as 3. For example, rubber, when it comes to almost all other surfaces, the mu for it is between 1 to 2. And mu between 1 to 2 means what? Means your friction force is going to be bigger than your pressing force N. Okay, so if you press them with 10 Newton, your friction could be like 14 Newton, 15 Newton. There is no reason that this friction should always be less than the pressing force. Okay, it definitely depends on the material. So the assumption that mu is always less than 1 is not correct. Now, a few other things, that terminologies that I want to talk about is, one, what parameters, what physical parameters would affect the value of this mu, whether it's mu s or mu k, where there are several of them. Definitely the top one is the material and the surface roughness, of course, because you know, the rougher the surfaces, the larger, the bigger these irregularities you have to overcome, and the larger the deformations would be. So those would contribute to larger forces. And then the type of the material, of course, as I said, some material will create some relatively large adhesions to the object they come into contact, like rubber. And so the adhesion portion of the friction could be large, or the nature of the surface of this material is most of the time rough. They are not like metals that can be very well polished to reduce friction or lubricated or something, right? So that's important, and that lubrication is also important, right? Whether the surfaces are lubricated or not, whether there is humidity, right? So if the surfaces are showing humidity, you can show that the humidity will affect the mu, okay? And also temperature. So most of the time temperature will increase in temperature is causing reduction in mu k. Humidity has kind of different effects. For some surfaces, when you make them wet, you are going to lose friction. For some, it makes the friction actually go up. Okay, so it depends on some other parameters. You probably all experienced that when you apply the brake on a wet road, your stopping distance is larger because you have a smaller mu k. Okay, but there are some surfaces that you probably have seen, if you make them wet and try to move them with respect to each other, you're going to get more friction. Okay, so it depends on the material, how humidity is affecting it. And sliding speed, as I said, typically the faster they slide, the smaller the mu k is going to get. And then area and the time of contact. Typically, for many material, the area and the time of contact means that mu s, the static friction, is going up because you are giving the surfaces to create molecular bonds. And more time of that, and then breaking that bond that is now over a large area and has been already formed is not as easy as if you didn't give them so much time and area to form them. Okay, so each one of these parameters would affect mu s, mu k, or maybe both. And in general, there are tables where mu is calculated, and I'll tell you that mu is always calculated experimentally. Okay, this formula that you saw, these Coulomb formulas, mu k or mu s times n, they are experimental formulas, empirical formulas, and mu's are determined for different combination of surfaces under different conditions experimentally. Okay. Now, a couple of other interesting things for you. One of them, if you ever hear the word tribology, tribology is the portion of the engineering, is the subfield of engineering that talks about friction and interaction of surfaces in relative motion. Okay, So it talks about how you can change the friction, how you probably can bring it down. Talks about lubrications, how the friction causes wear on the surfaces, and so on and so forth. And this is an important field in mechanical engineering where the reduction of friction is so important, like in engines. So car companies definitely are interested in people who know about tribology. Okay, so that's just a field. Just wanted to tell you the name of it. And another thing that I wanted to mention is this dry friction we talked about causes different types of instability in mechanical systems. Okay, like what? Like, for example, a brake squeak. Probably many of you applied the brake in your car or maybe on the bicycles, and you heard that big squeaking noise, right? Well, the reason is when you apply the brake and the braking pad is applied to the moving wheel, then what happens is the pad gets engaged, and then due to oscillations in the friction force and so on, the contact is reduced, so they might get off again and disengage, and then again engage and disengage. Okay, so this engagement between and disengagement and relative motion between the surfaces is basically set and reset several times, and that causes structural vibrations in both of them, and that will cause brake squeak. The other one is if I want to show you probably you all have seen Professor Walter Levin, and this former MIT professor, when he teaches, he uses the chalk and he creates dotted lines. Okay, so instead of solid lines, he can also create dotted lines, which is, I really liked how he's doing it. And the way he's doing it is by the due to instability of the friction that the friction causes between chalk and the board. So first, let's take a look at him.
Chromebook start fast.
Okay, look.
Now, if you want to draw far apart from each other, you go this way.
So as you can see, by changing the direction of holding the chalk, the angle, relative angles between the chalk and the board, and the speed that he's moving it, the relative speed, he's able to create those instabilities where the chalk gets engaged with the board, leaves a mark, then gets disengaged and lift off, and there is nothing, and then comes back into contact, another mark, and then leaves off, and again this pattern repeats, and then you will get what? You will get the dotted line, right? So that is one thing, and then as I said, brake squeak noise is another thing that you can check for yourself and see that due to instabilities of friction, the instability of that friction causes between the pad and the wheel, you will hear those squeaking noise. So I don't want to get into too much detail of each one of these, but just wanted to give you an overall idea of some of the negative effects of friction. You know, friction can be both positive and negative. It's a non-conservative force, so what it does, it wastes your mechanical energy, which is the sum of kinetic and potential energy, into heat, sometimes into noise, or both of them. And it wastes your energy. So if you have friction in the system, you have to constantly inject energy into the system to keep it working at the constant, let's say, momentum or whatever you have. And so in those applications, you definitely want to bring down friction as much as possible because it is not really helpful. But you can never really avoid friction. If there was no friction, guess what? We could not walk, we could not drive our car and everything, because that is what makes your car move forward, that is what makes you move forward, and so on and so forth. So friction is actually in many parts of the life is one of our best friends. So let's say here, this is our car, and let's say it is moving in this direction, and this is the driving wheel that you apply the torque to it, and this is the driven wheel. So it is rear drive. And let me also tell you this before finishing this video. One of the things I mentioned is the different directions of friction for the tires. So when you start the car and you apply the torque by applying pushing on the accelerator pedal, you're applying a torque, in this case clockwise, on the rear wheel to move the car forward. But you know, a torque is not what makes the car move forward. In order to move forward, you need a force forward to move the car. And where does that come from? Well, the thing is this: if this is the road surface, here, at this point of contact, where the motion starts, at this point of contact, because you apply torque, torque means what? Torque means it gives you angular acceleration, and angular acceleration means you will have what? Angular velocity. So this guy is going to start rotating in the clockwise direction. As it does, and in the beginning, since the center is stationary, because of the clockwise rotation, your contact point tries to move what? To the left with respect to the surface. And as friction is opposing this potential direction of motion or active direction of motion, what happens? The friction is going to be this way. And this is exactly that friction that will move your car forward. As you can see, this force is forward, and that makes your car move forward. So this is the mechanism through which the torque on the wheels is converted into friction, and it drives your car forward, and we call this guy traction. Now, if this is pure rolling without slipping, then the maximum friction that you can get here, because it is going to be static friction, there is no sliding, you might be able to get as much as possible, which is mu s times n, and we call that traction, of course, under the tire. Now, if you apply too much of torque here, which means too much of alpha, which means a big omega. If omega is too big, then you will have sliding here. Okay, and when this is sliding happening, that's probably what you experience under your tires of the car, right? That you, when you want it to start moving, you apply too much of acceleration, and instead of your car moving immediately, you see this tire starts to rotate in place and not moving too much forward, especially if this bottom surface does not give you a big mu s. Like you are starting your car on sand or on ice or something slippery, then this mu s is so small, so you have a very good chance of a lot of slippage here before your tire can get enough of speed to move on. Okay, so as you can see on the driving wheel, the direction of friction is the same as what? The direction of motion. Now, what about the driven wheel? This wheel here does not have any torque on it, okay? It's just driven. Now, how does friction act on this one? Well, so the sequence is this. First T, then alpha, then omega, and these are all fractions of time. Omega means trying to move relatively, which if the friction is big enough, then now you have friction. Friction means what? Means acceleration, because that's a force. So it gives an acceleration. Acceleration leads to what? To the velocity, which I have shown here. So now your car, the whole car as a rigid body, wants to move what? To the right. And that includes any point on this tire. Okay, any point on this tire wants to move with that velocity v forward. Okay, now here what we need to focus on is this contact point here. This contact point now wants to move to the right, along with everything else on the body, on the car. And what happens? Well, friction is going to oppose that. Friction said, no, I'm not going to allow that. So friction for this guy is going to be actually what? To the left. Okay, and what's the effect of that friction? Well, because that friction is to the left, that friction to the left with respect to the center, if you look at the moment of it, it will create a clockwise moment like this. And that T again means alpha, and it means omega for this front wheel, which is also going to be clockwise. So you see, that's why your front driven wheel will start rotating in the same direction as the driving wheel. But as you clearly can see in the beginning, the direction of friction acting on the driving wheel and on the driven wheel are in the opposite directions. Okay? And so this is what you have in the beginning of starting the motion. After that, when the car starts to move, it is all static friction, and it's not really affecting the energy of the system. And as you know, if we have rolling without slipping, when you have rolling without slipping, when friction is acting in either direction to this point, okay, if I call this A and I call this F, the work of the friction over a distance of delta S, whatever it is going to be what? It is going to be basically, although the tire moves, but the problem is you are applying your friction at every time point to the contact point, and you know velocity of this contact point is what? 0 if it's what? We call it is rolling without slipping. It means the contact point does not have a velocity. If that's the case, then the work of the friction does how much of work? The force of the friction. The small work done by the friction over a small distance, let me here use a small distance instead of a large distance. So first we look at the infinitesimal work, ds. It is going to be what? It is going to be the force F, and if I use x and y here, correct? So this is going to be F times I dot the displacement, right? But displacement of which point? It's not the displacement of the center point C, it's the displacement of point A. So it has to be multiplied by ds of point A times whatever unit vector that it has, let's say I. The thing is, how much is this dsi? ds of A? It's 0. Why? Because v of A is 0. You know, v of A, the definition of it is ds of A over dt. When this is 0, it means that the ds of point A is 0 for that point. And when you apply it here, it means it is not going to do any work. And now even if you integrate this over some distance from point S1 to point S2, still going to be 0. Okay, so the static friction, which is between an object rolling without slipping, this guy does not do any work, and so when it doesn't do any work, any negative work, it is not going to change my total potential plus kinetic energy. Okay, so friction does work when there is sliding. When this F is Fk. When this F is Fk, you have slipping, then yes, the work of the friction is negative Fk times delta S, where delta S is the distance traveled, and Fk is the mu k times N, and this negative one is because the friction is opposite to the direction of motion. So the angle between them is 180, and cosine of 180 is negative 1. Okay, but static friction does not do any work, and you do not need to spend energy to overcome that. But as I said in the beginning, when the car starts to move, the direction of this static friction is different for the driven and the driver. Okay, so hopefully I could discuss some important topics about the Coulombic or dry friction and the mechanisms for it, the formulas, the laws, and the graphs, and some other terminologies and important points. And thank you for your attention. See you in the next lecture.